Hey guys, so today we're going to be going over Gaussian elimination and Gauss Jordan elimination. So let's start with Gaussian elimination. The first step is to transform our linear system into a matrix. So we do that by first translating all the coefficients over and then the constants that it's equal to. So here our coefficient for x1 is 1. We don't have any x2, so that'd be 0. Our coefficient for x3 is -3. And then our constant over here is -2. This is called an augmented matrix. So here's some more coefficients, our constant, and then we have all of our coefficients and constants transferred over. Now for Gaussian elimination, we need to make this spot, and this spot all 0, so that we can then back substitute in and solve the system. So the way we're going to do that is we're going to start in here, we're going to move down and try to make this 0, this is 0, and then this is 0. So how can we make this a 0? Well, let's subtract 3 of this row from that row. So then we would get our first row is unchanged. Our second row is now this row minus 3 of this row, so that'd be 0, 1, because that's 0. This would be 9 plus -2, which is 7. 6 plus 5 is 11, and then our bottom row would be unchanged as well. Next, let's try to get a 0 in this spot, or this spot right here. So we can just add or subtract 2 of this row from this row, or 2 of the top row from the bottom row. So that would be, again, our top row is unchanged. Our middle row would be unchanged as well. But our bottom row would be this row minus 2 of this row, so that'd be 0. That's a 0, so that's unchanged. 3 times -2 is 6, so that'd be 7. -2 times -2 is 4, so this would be 8. Finally, we need a 0 in this spot right here. So we can subtract 2 of the middle row from the bottom row to achieve that. Again, our top row is unchanged. Our middle row is unchanged as well. 7, 11. Our bottom row, 0 times -2 is just 0. At 0, that's just 0. -1 times -2 is -2, so that'd be 0. 7 times -2 is -14, so that'd be -7. And that's -22 plus 8, which is -14. So now we can just transfer this back to our linear equations in the same way we transferred our linear equations to an augmented matrix. So this is just our coefficient of each variable, and then this row right here would be our constants. So x1 minus 3x3 equals -2. So there's no x1, so we start with x2 here. x2 plus 7x3 equals 11, and then down here we only have x3, so 7x3 equals -14. Now we just solve. So we can start with this equation. It's pretty obviously divide both sides by -7, so x3 is 2. We can plug our x3 into our next equation right here. So let's bring this up. x2 plus 7 times our value for x3, which is 2, is 11. So then x2 equals, this is 14, so this would be -3. And then we can again plug in our x3 for this equation right here. So x1 minus 3 times 2, because that's our value for x3, equals -2. So then x1 equals, this would be -6, so we'd add 6 to both sides, and we get x1 equals 4. So here is our answer, using Gaussian elimination. Next we're going to solve this using Gauss Jordan elimination. So the original steps of creating a augmented matrix and then getting zeros in these 3 positions is going to actually be the same. Now instead of going back to equations, we're just going to try to not only have zeros in these positions right here, but also get zeros in these positions. So that we'll only have, and then ones down this diagonal right here. So that we know that each variable is going to be equal to, when we transfer back to our equations, each variable will just be equal to its answer. So the way we can do that is, well, luckily for this problem we already have a 0 here, so that's nice. Next, let's try to get a 0 right here. So as you can see, the bottom equation plus the middle equation will actually give us a 0 because we have a 7 and a negative 7 there. So let's make our next matrix. Our top row is going to be unchanged. 0, negative 3, negative 2. We're going to add our bottom row to our middle row. So that's 0, 1, 0, and then negative 3. And then let's, our bottom row is unchanged. 0, 0, negative 7, negative 14. So next, let's simplify. Our bottom row we can just divide by negative 7, and as you know, it's one of our basic operations that we can do on matrices, so let's do that right now. So again, top row is unchanged, middle row is unchanged, oops, sorry, negative 3, and our bottom row, now both are divided by negative 7, so we have a 1, and we have a 2. Finally, we just need to get rid of this negative 3 up top, so let's add our bottom row to the top. Sorry, this is a little messy. I'm going to put our final matrix up here. We're just going to add our bottom row to the top, so that's 1, 0, and then 3 of that makes 0. So 3 times 2 is 4, or 6, add to negative 2 is 4. So up there, 4, 0, 1, 0, negative 3, and then 0, 0, 1, and we have a 2. So transferring our augmented matrix back to equations, we get x1 equals 4, x2 equals negative 3, and x3 equals 2. So as you can see, we got the same answers using Gauss Jordan as we did just Gaussian elimination. So if, like, for your problems that you're doing at home that don't have these exact same numbers, let's say you have your matrix of, I don't know, some random numbers. So for Gaussian elimination, we're going to always want to go in this order. First we make a 0 here, then we make a 0 here, then we make a 0 here, and then we can go back to our equations and solve from there. For Gauss Jordan, we do that same 0 there, 0 there, 0 there, and then we want to make a 0 right right here, and then right here, in that order. And that's just the easiest way to go about it, in making sure that each thing is, like, easily solvable. So, alright, thank you.